happy to introduce Henry Snowden, who will be telling us about LightMatter.jl, LightMatter.jl, simulation of light-driven hot carrier dynamics. Take it away, Henry.
Yeah, hello. Thank you very much for inviting me, and I hope you don't get too sick of my voice, as I do have 2 talks this afternoon. I apologize for this. But first of all, I'm going to be talking about simulation of light-driven hot carrier dynamics, which basically means the response of electrons to a laser pulse. And if you aren't really aware, we're trying to move towards a green and more sustainable future, and light is a very important part of this because it's very abundant. Obviously, we can source it from the sun, and if we can channel this into chemical or electrical energy, we can easily produce much more sustainable processes for our future. But the problem with this is really designing materials that are very optimal and efficient at this is a great challenge, and this comes down to our ability to sort of simulate their response to the light itself. And for anyone who's not really aware and hasn't studied this field, I wanted to quickly go over the timeline of a light-matter interaction so that you both know sort of what's involved, as well as how long these processes take, and so how long a duration of a simulation you really need to perform. So we obviously start off with an equilibrium Fermi-Dirac distribution. I hope most of you are familiar with this. And when we hit it with a laser, electrons start to absorb photons and enter an excited state. And this generates some electron-hole pairs, cartoonishly depicted as a step, but very rarely actually look like this. And this takes on the order of tens of attoseconds to a few femtoseconds. So very quick reaction. These then start to interact with one another and the thermal background of electrons, and they start to produce a hot electron distribution you can see here, which is just a Fermi distribution at a higher temperature. And this again can take on the order of 10 femtoseconds to a picosecond, but in all metals it will be sub 100 femtoseconds. And finally, they will then go on to interact with the phonons, and now we're into the sub 100 picosecond range. So we need methods that can simulate attosecond processes all the way up to almost, hundreds of picosecond processes. And this needs to be simulated in one process, and that's quite a challenge to do. Why do we need to do this? We obviously want to make use of these excited materials. And in my later talk, I will discuss a little bit about atomistic simulations using laser-driven techniques. But really, there's 3 main ways that an excited distribution can interact with a material or an absorbate on a surface or a quantum molecule in a quantum gate. It could happen via direct excitation, indirect excitation, or spillover into the LUMO. And all of these methods are highly dependent on the current exact electronic distribution in your material, our red thing here, and therefore accurately depicting this is essential if you want to get any level of rates or chemical reactivity correct. And so the aim really of LightMatter.jl was to be able to simulate these processes efficiently and in an open source way that anybody, experimentalists or computationalists, could use to investigate their materials. Now, it's not the first code that can do this, and I think that whenever you start thinking about making a new code, you should first survey what's out there and see if it's good enough. Otherwise, we end up with millions of codes and they all do the same thing. And there are a few examples, including quantumoptics.jl, that I have manipulated to do these sort of things, but they all sort of have issues. Quantum optics, being a full quantum treatment, means that it doesn't scale very well to nanoscale properties that we're interested in. We have other techniques such as ELF-BOLT or NTM-Pi that are really limited to one methodology. They can't provide you a list of options, and that I also think is a real issue. And so what LightMatter.jl shines or tries to do is it tries to offer you a multitude of methods and approximations within these methods that allow you to design the exact simulation you want to perform. We make no decisions for you, you get everything you would like. As part of this, we want it to be easily extendable, as if you have any new techniques or methodologies of interest to you, then we want you to be able to easily plug and play them in and start to mess around with it. And again, we really don't want to limit what you can do. And then finally, we want it to be extendable enough that it can model a wide range of systems of varying complexities, including surfaces, alloys, whatever it might be. We want to expand far beyond anything that is currently possible. Julia can assist with this. It is a very powerful tool, and there's 3 main ways. First of all, metaprogramming with expressions is an incredibly cool tool that we have fallen in love with recently for assembling your equations and your functions on the fly. We use generalized generated along with the metaprogramming tools directly in Julia to physically step-by-step Lego block assemble exactly what you asked for in equation form and then provide you that function to then propagate through ordinary DiffEq or whatever else you like. The flexible and high-level code structure of Julia also makes it so that anyone with very little experience in code can somewhat get to grasp with the package. I really like that. I mean, maybe some people will get mad at me here, but the code is quite Pythonic in the way it looks, and everybody knows how to write Python code. Find someone who can write Fortran 77 code. And finally, the multiple dispatch and nested structures allows us to do these complicated systems without limiting to is it this system or if-else sort of statements that might limit performance. The current methodologies that we obviously want to potentially implement are the two-temperature model. Any engineers will be very familiar with this model if you're interested in this field. All it does is it says your electrons are a temperature bath, your phonons are a temperature bath, your electrons get heated up by a laser, and then they sort of cool down. This is extremely cheap because it's extremely classical and sort of basic, and so you can do huge spanning complicated structures, multi-dimensional, whatever you want, but this comes at the cost of really none of them electron hole pairs that we might be interested in. The other side of that coin is time-dependent density functional theory. This is what I call the quantum approach to this problem, and it provides very accurate electron hole pair generation at a significant cost, but it is unfortunately unable to capture electron-electron scattering at all, really. It puts electron-electron scattering on the same sort of timescales as it does the electron-phonon. And this means that these non-equilibrium electrons are living far too long, and any resulting reactions you propagate the rate will be completely off. And finally, what I consider to be the state of the art is the Boltzmann equation. This provides accurate dynamics of the electron and phonon distribution, but it is excessively expensive, like beyond belief, at least in my opinion, which means you cannot go beyond a 0D, very simple system with no sort of added complexity external fields. It blows up to in expense far too quickly. And before I could even make this package, I had an issue, because I wanted the speed of the two-temperature model and the ability of the Boltzmann equation. And so I wrote like 4 lines of Julia code and then went over to a chalkboard and along with the Rethfeld group built a whole new theory of light matter interactions to accomplish this problem. And for the next 5 minutes, I'm going to briefly introduce this. So if you don't care about physics, just go to sleep. That's fine. So the athermal electron model takes this sort of total electron distribution you might see from a Boltzmann calculation and sort of just cuts it in half. This is a very nice feature because now we have a thermal distribution that we can represent as a temperature, and this difference from our true distribution, our electron hole pair distribution. As we have a temperature system, we can treat this as a temperature system, and I've made a two-temperature model. Woohoo, it's cheap. Now, if I just plug on an electron hole pair distribution and add a few approximations on top, this becomes this little assembled system that is much cheaper to run than a Boltzmann equation and therefore provides me the flexibility to go bigger, harder, and more complicated than we ever really could before. And as well as this idea of plugging an extra system on top is what then motivated the design structure of LightMatter. We wanted to just plug things on top of other things or insert approximations in places. And so how LightMatter is really designed is that we provide you with these building blocks, some electronic systems, some phononic systems, and some structural choices that you can make. You just say, I want this and that and the other, and it builds a simulation. And just to quickly, or to show you sort of how this process works, to build a very simple two-temperature model, we first are going to design a laser. We're going to choose a Gaussian laser because everybody does. We're going to give it some parameters. This all works with unitful, so you don't really have to care about units because units are annoying. We're going to build an electronic and a phononic temperature by setting them to true, coupling them, or setting the couplings to do, giving a couple of approximations and the relevant parameters. Pop that all into a simulation object, and we're done. We have now built a 2TM. We can ask the system for the equations, and this is the equation of motion for the electronic system. It looks like a mess because the other thing I realized was expressions look like a mess very quickly and become quite hard to read, but that's fine. You'll figure it out. And we set some initial temperatures, a time span, and then we just run our simulations. It's all plumbed through DiffEq, so all the keyword arguments, all the algorithms that work there also work here. So you really can go straight out the box. And we have some post-processing stuff, saving as a HCF5, and there's a whole host of different functions or symbols you can place here to get internal energies out or various different properties to make your life a little easier. We can then obviously get the results from this. This helps you by just breaking them all down into nice vectors and matrices. Otherwise, they can be quite awkward as we use recursive array tools under the hood, and this produces quite awkward solution objects if you ever try to do that. And what you produce is a two-temperature model curve. Here, it doesn't move down very far because I simulated gold, and gold doesn't have much of electron-phonon coupling, and so if I really wanted to get this to go into equilibrium, we'd be going for like 20, 30 picoseconds. And this is part of the problem. We wanted something that could really scale, because if you want to go 20, 30 picoseconds, I will show you some computational costs later, but Boltzmann isn't going to do this. To include athermal electrons, all we have to do in the systems we've already defined is define a photon frequency and just say that they're now coupled to athermal electrons. And now these baths will go, okay, I'll just assume that's there. We need to define an electron distribution to propagate over, a density of states and a geometry, just so that it knows what the electronic structure of your problem, and build an athermal electrons. Unfortunately, this is a bit more complicated, but you again set it to true, set all your couplings, set your approximations on how you want things to relax, and then give it the relevant parameters. It's the same process all over again, and now if we plug all of this into our sim, we now have an athem model rather than a two-temperature model. We could have substituted all of this out for an electronic distribution object and a phononic distribution object, and we'd have a Boltzmann equation. And you can really just pick and play however you choose, and it will build whatever you want. And here is the difference in results. There's a slight decrease in temperature because the temperature is now stored within our electron hole pairs, and we get access to the actual electron hole pair distribution as a function of time. This is at the peak of the laser pulse. And so this is just the part that's completely missing from your two-temperature model. Now, if any of you are aware of light-matter interactions, you might tell me, why don't you just use the Boltzmann equation with a relaxation time approach? It's a common approach that's been used since like the 70s, I believe, and I'll tell you because it has horrible energy and particle conservation problems, and I have no idea how no one figured that out. It loses about, I think, over a picosecond up to sort of 80% of the internal energy that was put into it. So it massively bleeds energy as well as particles, and therefore it's not sufficient to capture long-time dynamics. In the short time frame, sure, you could do this, but you can't do this for the 20 picoseconds of gold, and so really we did have to build this whole new theory. Of course, athem does not lose particle or energy conservation. If it did, I wouldn't be here, so, you know, take my word for it, we fixed the problem. And it compares well. In terms of excitation, it is almost exact to the Boltzmann equation. In terms of relaxation, it's not quite so exact to the Boltzmann equation. But all of these calculations, here's the cost. So 1 core and about 2 minutes to perform this athem calculation. This was about a picosecond, and 160 cores and 5 hours to perform a Boltzmann calculation. And this is obviously just going to scale worse and worse and worse as soon as you start to add spatial degrees of freedom. It's just not possible with the Boltzmann. You're going to destroy your entire CPU budget in about 1 calculation. And so, just to sort of summarize this model, it really does capture electron dynamics similar to full Boltzmann collision integrals. It does it cheaply and doesn't violate physical laws, which I always like. And if you'd like to find out more about real details of how it works, there is a preprint that hopefully should get accepted into, well, it's accepted into applied physics, so hopefully will eventually be published one day. And a key part of this is this method is only publicly available in LightMatter.jl. So anything I'm about to show you with all the cool stuff that we can now do that nobody else in the world can do, well, they could if they, you know, went on Julia and clicked add LightMatter, but without it, they can't do any of this. So I've said we want to go harder and bigger. So how do we do this? So to go beyond 0D, we need to add a fixed law diffusion that you might remember from your physics or chemistry classes, and some ballistic transport and non-equilibrium electrons. I'm going to ignore phonon transport because it's so slow that I'd fall asleep. And here's the big deal, right? As soon as I go to a 30 nanometer thin film, which after sampling a bunch of literature was approximately the average size that experimentalists were using, I saw a decrease in the surface temperature of about 25%. This is obviously going to be a significant effect if what you care is the energy of your surface. Having 25% less energy at the surface means whatever you think that energy is going to do, it's going to do 25% less, if not worse. And so really incorporating these spatial effects and properties is important into getting realistic simulations of our materials. And to really push this, one thing that you can do within LightMatter.jl is you can give it a range of density of states that correspond to your surface all the way down to your bulk, and you can actually see the effects of changing the electronic structure as you go through the material on your temperatures and spectral densities. Here I've tested a lot of materials and a lot of surfaces, and just given the number of electrons at 1 eV above the Fermi energy, I think at the peak of the laser pulse. And you can see for the most part it doesn't really matter, at least at this energy range, but clearly for ion 111, about a 1.5 times increase in number of electrons is a big deal. And again, this is an important factor to include, and it's not something that you can include or incorporate in anything other than TD-DFT and ATHEM. They're the only two methods that could ever capture this effect. And TD-DFT is really size limiting. Small nanoparticles, tens of atoms only. You go bigger, it's too expensive. So this is really something that can only be done here. And if you want to do this, you simply just need to tell it now has a spatial density of states, give it a folder where it can find them, and give it a geometry of where you calculate them so it knows the heights that each of these correspond to, and then it will interpolate and map everything onto the grid that you chose. And so it handles everything on the hood to build these more complicated electronic structures for you, so it's no real big deal. And for the conductivity, you set it to true, like everything else, and you give it the respective parameters that it asks for. All of this sort of parameter request is in the documentation, so don't worry about needing to memorize the equations and know what parameters you need. And just to sort of cap off a little bit, I wanted to show an antenna reactor complex because this is a material that is very interesting in plasmonic catalysis at the moment, and is a material that this study we recently submitted to Nature Materials, so it's apparently exciting. And really these materials are categorized by having an optically active material that interacts with your laser and a catalytically reactive material that interacts with that is your surface, that interacts with some adsorbates or molecules or whatever it might be. And so in order to do this, you now really need spatial transport, because physically here, if we want to resolve the difference between our gold and our nickel, we need to be able to say, okay, at this height into our slab we have it's gold, this height we have nickel, and so Boltzmann and any of these things aren't going to be able to do this. And already at this sort of size, we're pushing the limits that TD-DFT or anything like that could possibly simulate. On the right, I have the temperature profiles at the surface of the nickel. Unsurprisingly, gold would be the highest if this whole thing was gold, and that would be because it has no electron-phonon coupling, and so it just stays hot forever. Whereas the nickel itself, due to the incredible electron-phonon coupling throughout, if this whole thing was nickel, it would just all go straight into the phonons, and you would have no real electronic energy, and our gold-nickel hits that sort of perfect sweet spot of being quite a lot hotter than nickel, but still reactive and interesting, unlike gold. And we can do the same thing to look at our athermal electrons using the ATHEM model, and you can see a huge spike in comparison to both the gold and the nickel, showing that this material is much better at transporting electron hole pairs to our surface, where they can be reactive and useful, than any either the gold or the nickel on its own. And again, this is very interesting to materials discovery or any processes like that. And to do this, we need to add our interface height onto our dimension. We need to tell it that it has two systems, and then all of our material parameters, I've kind of tried to make it simple up here. Instead of just giving it one, we just give it a vector of length 2. And then it knows from this interface and how many systems you have that, oh, that height denotes to that parameter, that height denotes to that parameter, and so it then again handles everything under the hood for you to build much complicated systems. And you could even go all the way up to building photovoltaics, where you have all the different layers involved in a photovoltaic stacked on top of each other, hit the light on one side, and watch how the electrons move all the way through all of them, and it could all just be mapped out directly through ATHEM and through LightMatter.jl. And so these were my aims, really, and I thought I would just come back to them a little bit and discuss sort of how we're doing on each of them. Oh, apparently not. So LightMatter includes methods from all levels of theory. We do have a dipole approximation density matrix approach. It's a little bit work in progress, so don't expect it to be too accurate just yet. All the way down to our classical 2-temperature model, we can do it all. Adding new methods is literally as simple as defining a new keyword argument or changing the symbol in that conductivity approximation or whatever it is, and making sure all the relevant parameters are there, building a new expression, and it all works throughout. And we've already shown that you can implement methods to capture a wide range of complex systems, antenna-react complexes, you can look at surface effects, and like I said before, this is all stuff that until now has not really been feasible. And so hopefully with future development, this package could become very interesting. And I will say it's only a year old, so let me off on the docs and tests. It's not quite there yet. So thank you very much for listening. I hope you're not too bored of my voice yet, because in about an hour you've got me again. I'm so sorry. And if you want to learn more, there's the GitHub link.
Thanks very much, Henry. Do we have questions from the audience? We have plenty of time.
Thank you for that very interesting talk. I have a question about your electron-hole pair treatment.
Yes.
Do you include screening between the electrons and holes, or you treat them as independent particles?
Do I include spin?
Do include screening?
Oh, screening. So at the moment, we kind of treat them as independent particles, but there is already methods sort of being developed to include more complicated matrix elements in how that excitation is done. One of my aims is to use TD-DFT to actually get the matrix elements straight out, and that way we should be able to reflect exactly TD-DFT's electron hole pair excitation profiles, so that amazingly good at it no longer becomes true, it becomes equally good at it, and use that to then drive our electron hole pair generation. Okay. So it's possible, but not yet.
So just to clarify, the pair density of the electron hole pair that you showed, so that is an uncorrelated density then?
So it's uncorrelated in the sense that the excitation isn't screened based on the particles, but it's correlated in the fact that it is scattering among the other particles, and it's correlated in the fact that in the Fermi's golden rule expressions we use, it does incorporate things like Pauli principle, etc., to ensure.
Yeah, but the pair density you will be able to factorize it as an electron density or a quasi-electron density times a quasi-hole density.
Yes.
Thank you.
Thank you for the talk. In the athermal electron approach,
yes,
you split up the density into two parts, the thermal and the athermal, right?
Yes.
How do you choose the temperature for the thermal part?
So what we do is we choose it to start out as the starting temperature, and then we use a 2-temperature model with an addition. Rather than using a laser source term, we say that the energy into this system is the energy given out by scattering here. So this term represents scattering of the electron hole pairs with the thermal system, and any energy lost from here then gets through this process, then gets moved into here, and then converted as a temperature.
I see.
Yeah, a related question, to what limit or extent this separation breaks down?
Okay, so there's two main approximations. So, this separation it can be derived exactly. There is no actual issue with separating it, because you're just saying that my distribution is a sum of distributions. And if you were to include all possible interactions between these systems, then it would still be analytically exact. The only place that this really breaks down is, for simplicity's sake, we actually say that currently the athermal electrons don't scatter with themselves, just because there's, at any one time in a realistic system, there's so few of them that this scattering is minuscule in comparison to the scattering with either the phonons or the temperature system, and therefore we can just save one extra step of calculation.
So you mentioned photovoltaics as well, which is a subject near and dear to my heart because that's what I focused on during my own PhD. And I'm curious, so your examples here were all with lasers, which of course we presume are monochromatic or close to monochromatic. Are there any particular complications that would arise if you're talking about excitation with like a solar spectrum, for example, where you have a wide range of photon energies?
Funnily enough, the thing that just got submitted to Nature Materials actually includes using a xenon lamp. So we actually already have incorporated methods to use these like solar spectrums or anything like that. That's already incorporated and ready to go. But for these images, I just used a pulse because it makes, I think, more sense to most people.
Sure, makes sense. And that you're still able to use the same like thermalization models and everything,
Yes.
even when you're exciting at a wider range of wavelengths.
Yes, because so if you treat, basically how we treat these wide range of wavelengths is we say, okay, we basically take your lamp source and break it down into bands of certain finite frequencies and say, okay, we have this many photons per time step of this frequency, et cetera, et cetera. And so this in total builds up this one mass excitation.
Gotcha, makes sense. Other audience questions? We do have a couple minutes still. Yeah.
So when you subtract out the thermalization from the reference, then the plot that you were showing about the electron-hole pair distribution.
Yes.
In principle, some part of it can be negative.
Yes.
So how do you interpret that as a probability or a probability density?
So the negative part, as in if you're referring to like this here.
Right.
The negative part of this is the holes. So it's basically the missing electrons that have moved over here.
I see. So that will be the hole density, and
Yes.
the other
So
one will
the
be
negative part is the hole density, and the positive part is the
Okay.
electron density.
Thank you.
Last call for audience questions.
Very simple question. You were talking about when you supply the density of states at different layers, you interpolate in between. Do you have to be careful about how you do that interpolation at all, and like what method do you use for that I've done a lot of interpolation. It's always trickier than you want it to be.
Yes, you absolutely do. I mean, the biggest and the most difficult part, I think, of that interpolation is caring about how well resolved the density of states that you've provided it are. So really, I would recommend that if you're going to use a method like this, you need enough densities of states in that folder to go all the way from surface to bulk, like every atomic layer. With that, then it becomes reasonably simple, and the interpolation, all it's really doing is saying, okay, my grid point happens to be actually halfway between two atoms, but the difference in densities of states is so similar at that point that it doesn't really matter too much. If you space that out to save yourself some DFT calculations, then you get some really funky looking densities of states.
All right. Any last questions? If not, I'll invite Weishi to come up and get set up, and we can thank the speaker one more time.